Right, I'll just get started. Okay, so I mean, contracts are about runtime validation, and sometimes that validation is going to fail. And when it kind of fails, you hope that there's some blame tracking, and you hope that your blame tracking is correct, because if it's not, you get into this situation where you don't know who's who, you don't know who's responsible for which part of the contract, and this is actually going to give you some incorrect results at times. And so this work is really about getting blame right, particularly for intersection and union contracts, and this talk I'll be mostly focusing on intersection. So what's the context? Well, quite often we want to add contracts to untyped programs. So this is a JavaScript program, and we have a library, and we have a client. And so our library is going to export this function f, and when the input is a number, it's going to add 100, and then otherwise, it's going to perform Boolean negation on the input. And so our client might use this function in various ways. So for instance, it might pass a string, and this is actually going to give us a result back, but it sort of relies on JavaScript implicit coercions, and so we probably want to avoid that. But the other two, they seem reasonable, so we pass it 42, we get back 142, and then true maps to false. But if we want to try and add contracts to this program, one of the challenges with contracts and adding them to untyped programs is that these untyped programs often use very dynamic and reflective behavior that can be hard to describe using contracts for kind of like simple types. So for instance, here I've added an interface between the library and the client, and we might try and add a contract here, and as a first go, I've added this contract that says it's int to int. So what happens if we try and apply that? So we start with the integer argument, and so what's going to happen? Well, we take our wrapped function, and then we're going to apply the wrap rule, so that essentially wraps the argument using the domain contract, applies the function, and then it's going to wrap the result using the codomain contract. And so this all works out okay, so the domain contract succeeds, we get the result, and then the codomain contract also succeeds. But in the case of the Boolean argument, what's going to happen? Well, we're going to get blame, and specifically we're going to get negative blame. And that says, well, actually it was the client at fault. So we do the wrapping as before, but then the domain contract is going to fail because, well, it's the integer contract for a Boolean argument. So this isn't really what we wanted. We had some of the behavior, but not all of the behavior. So I might try another contract. So now we've got this Boolean to Boolean function. So what's going to happen here? Well, kind of the story is similar, but perhaps reversed. So for our integer argument, we're going to get blame, negative blame. So the client has given an incorrect argument because obviously 42 doesn't respect the Boolean contract. But then for our Boolean argument, well, we get the right result here. So we do the wrap rule, we then evaluate the function, we apply the codomain contract, and we get back false. So that's good, but I mean, in either case, we haven't quite got the behavior we wanted. We didn't quite have both behaviors, and really, we want both function contracts. So that's where the intersection comes in. So we say this function, well, it's a function from int to int, and it's a function from bool to bool. But when we think about how to sort of monitor these contracts and sort of do the runtime checking, well, we have these rules, and so we think that having uniformity in these rules is a nice property. And by uniformity, I mean when you decompose the contract, for instance, this function contract, I don't really care what A and B are. I don't want to peek inside A and B. I just want to look at the outermost contract operator. So here's the wrap rule by Finland and Verleisen, which is kind of the sort of foundation of higher order contracts. And so you take a function contract, and when you apply it to an argument, you're going to wrap the input with the domain, and then you'll apply the function, and then you'll wrap the result using the codomain. And so kind of a piece of important information here is that what I call a blame node is negated for the domain. And the reason is because the obligations to follow that contract are inverted. So if the library was responsible for providing something from A to B, then it's actually the client that is responsible for providing an A. And then it's the library that is responsible for returning the correct result. But what about intersection? Well, we would like a nice uniform rule that doesn't care what A and B are. So we might say, well, to monitor something that's A intersect B, we just monitor against A and then monitor against B. So we split them like that. But if we sort of follow that through, what happens? Well, let's go back to our example. Now we've got the intersection contract. And so if we go through each of our uses, starting with the string argument, so what will happen? Well, we're going to split the intersection like we wanted, and then we'll start doing our wrappings of the function contract, and that works out to in. So we start with the Boolean function contract, and that's going to give us a negative blame error because the string argument is going to fail the Boolean domain contract. But that's what we wanted. We wanted to get rid of that kind of implicit coercion case. But what about the integer case? Well, again, we will split the intersection, and we start wrapping from the out to in. So we start with this function contract. And of course, the integer argument is going to fail the Boolean contract. And so we get negative blame, which isn't really what we wanted. And it turns out we're always going to get negative blame. So for the Boolean example, we do a bit better with our wrappings. So we actually get past this one, but then we'll hit this one, and we'll get negative blame again. So something isn't quite right here. And so to sort of work out what's going wrong, we appeal to the insight by Cullen Tiemann, who first looked at intersection and union contracts. And so the really important thing is we want to distinguish blame between the library and the client and how we actually interpret blame for the library and the client. So in particular, for a library to respect an intersection type, it has to respect both components, which is what you might expect. But then for a client, you actually respect, well, A or B, or both, but it has to be at least one. And so the kind of intuition for that is, well, if I'm a client and I'm receiving a value that is an intersection type, I already know that it's both components. I know it's A and B, so I should be able to pick and choose which I want to use. And this or here is actually really interesting because it now opens up the possibility of having violations as you evaluate a program, but that might be okay. So previously, as soon as you had a violation, a contract violation, things usually ground to a halt and you would just throw an error. But now you can no longer do that. You actually have to be a bit smarter with how you sort of interpret these violations. So taking this idea about blame, how might we have this for uniform monitoring rules? So we now have these kind of modified monitoring rules, and the key idea here is that we add provenance to our blame nodes, so the things that are attached to each contract. And so for functions, we have this path variable, what I call a blame path, and then whenever we apply a wrap, we're actually going to extend the path with these markers that tell us, well, is this the domain contract or is this the codomain contract? And importantly, we have these numbers here, n, and that is going to tell us which use of the function contract it is. So this is the extension operator, which I'm just going to leave abstract, and I'll show some concrete examples. But it's really about sort of tracking a path through as you apply function contracts, so you can sort of link the subcontract back to the original function contract. And then for intersection, well, we're going to view intersection and union types as sort of binary trees. And then whenever you decompose an intersection, you're going to create these branch nodes. So here we have a left branch, and then we have a right branch, and they both have a parent. This should be nil, sorry. This should be p, sorry. But in each case, the paths here actually start out as nil. So this is the empty path. So as soon as you decompose, you have empty paths because you haven't done any function wrappings yet. But then, of course, these can be extended as you wrap. So let's take this and then try our examples out again. So we'll start with the string example. And note now we have this violation set at the top. So as I said before, it's no longer okay to just stop as soon as you hit a contract violation. You need to collect this information as you evaluate and then kind of interpret it until you have enough evidence that you can say, well, actually, now I know something really has gone wrong. And then, so we have our contract here, and I'm going to put the blame nodes just on the right, but they can essentially be inlined. So we start by splitting our intersection like we wanted. So we have these two branch nodes, and then we have our two subcontracts. And now we can start wrapping as we did before. So we start out to in. So we create these two new subcontracts for the domain and codomain, and note how the paths now have been extended. So this tells me in the right branch, this is the domain contract, so that's for this one here. And then in the right branch is the codomain contract, and that's for this one here. Now we have an actual contract to evaluate, this one. But that's actually going to give us a violation. So we have now blame on this node here. And so we have to ask ourselves, have we actually got enough evidence to say, well, we need to stop? And if we think back about how we interpret blame for intersections, and in particular how the client can use an intersection, because this is negative, so that's the client. Well, the client can use one or either one or both. So it actually has the choice, and so it's okay to violate one as long as you respect the other. So this isn't actually enough evidence for us to say we need to stop. So we can carry on evaluating. So now we have a contract violation, but we didn't stop. So we carry on evaluating, and now we can do another wrapping. So this is of the second function contract. So we create some more blame nodes for the left branch here, but it's still the path extension. And now we have another contract to evaluate. So we have this integer contract here, applied to the string. But this is going to cause another violation. So we add this to our violation set. And now we have another question to answer, which is, now do we have enough evidence to throw an error? And so if we kind of have a look here and consult the blame nodes, we can see that we have this match on both the left and right. So the left branch has raised negative blame, and the right branch has raised negative blame. And importantly, they match. So these zeros match. So it was in the same use of the function contract. Now this is actually enough for us to say, well, the client, it didn't pick either one, it decided to pick none of them. So that's actually an error. And so now we have this blame, negative blame, and then we lift that out, and this is what we wanted. We kind of wanted to have blame when you pass the string to this function. Now we can try another example. So we've changed the input, so it's this integer 42, and it starts off very similar. So we split again, and now we can start doing wrappings out to in. So we have these two nodes here, and again, so this is essentially the same. Now we have a contract to evaluate, and this is going to give us blame on this violation here, because 42 isn't a Boolean. And so we have the same question to answer. Is this enough evidence? And it's not, because we only have a single violation when we need violation on both branches. So we carry on. We now have another function to wrap. We create some more blame nodes, and we're in another state here to evaluate a contract. And now we actually have a contract that will succeed. So we don't get any violations for this. We just it just succeeds and goes away. And then now we have to apply the function and sort of evaluate the codomain contracts. And I'm kind of sort of going to skip over these details, because you might think, well, one of these codomain contracts is going to fail. There's some machinery to say, when the client has already violated a contract, then the library is allowed to violate some contracts. And the details of that are in the paper, but you'll just have to take my word for it that this comes out okay. And then you can try for this one. I won't go through all the steps, but it's essentially exactly the same, but the violation is just on the other branch. So we do the split, do some wrappings. Here we get a violation, but it's not enough evidence. And then again, there's going to be some sort of magic going on here, but it's essentially, the intuition is, when the client has decided to not do something, then the library is allowed to not follow it as well. So in all three examples now, we've got the correct behavior, and the kind of key idea is the provenance of these blame nodes in conjunction with the state that collects the violations. So what else is in the paper that I haven't had a chance to talk about? Well, one thing is that we define this new notion of contract satisfaction, which is just in terms of blame. And so the intuition there is to say, well, a library satisfies a contract if, for all possible clients, you can't get positive blame. And then a client satisfies a contract if, for all possible library implementations, you can't get negative blame. But that alone doesn't tell us very much about the behavior of our contracts. We could have some really ridiculous contracts that don't actually check anything. So we supplement that with some properties about contract satisfaction. So a basic example is to say, if a library satisfies a contract A and a library satisfies a contract B, then the library should satisfy the intersection contract A and B. And then, of course, there's union contracts, which I haven't really talked about, but there's a full account of that. But to give a sort of overview, it's essentially dual to intersection, which is what you might expect. So for a union contract, the library can respect either one. There's a choice here, and so this OR again introduces the possibility of having intermediate violations that don't necessarily trigger sort of a top-level blame error. But then the client here must actually respect both. And the idea here is to say, if I'm a client receiving something of union type, I don't know which one it's going to be, so I have to be prepared for both. And then kind of finally, so we added this provenance to work out, which Spider-Man, violated the contract, and this is good. But there's kind of issues, well, getting the right answer is one thing, but if you're waiting around for the answer, it's not so handy. And as we saw in the previous talk, there are kind of serious issues with performance in some cases. But none of this is really looked at contracts that have all this state and provenance. And so I guess kind of main future work and the main interesting future work would be looking at how drastic this style of contract monitoring would affect performance. But I think it's interesting. I think there's a lot of low-hanging fruit for the optimizations with these intersections and unions. And with that, I'll finish. Thanks.
Questions?
Cool work. I wonder if you have a contract, say, intersection of unions, and you have an equivalent form in distributed form, would you have the same exact path for checking contracts, or they would be different?
So the behavior should be the same. So if they're kind of equivalent according to some distributive laws, they should give you the exactly the same behavior. So previous work by Kyle and Tiemann, they actually relied on the distributive law to monitor these things, but that involved sort of duplicating some contracts, whereas we sort of don't necessarily have to do that. But yeah, it shouldn't have any effect on the semantics.
But you could have a different representation, and one of them would be probably more efficient than
Yes,
the other.
so yeah, in terms of efficiency, there's differences there, but in terms of correctness, it shouldn't matter.
Okay, thanks.
Hi, cool work. You said that it's basically future work to look at the performance, but I was wondering if you could speculate, because I see these intersections and then I see basically a split, and you have these different things that you can try out, these different contracts that where one only has to hold. If I have multiple of these calls that have these intersection types, don't I get an exponential blow-up?
Yeah, I don't know the complexity. I think it's probably roughly proportional to the size of the types, but then of course that's not assuming that these things keep crossing the boundary as we saw in the last talk. So yeah, I don't know if I wouldn't want to say that I don't know the time complexity of this, but there's one thing that we don't have is recursive contracts, and in that case then you might start getting kind of this unbounded memory consumption with the provenance, so that's kind of one potential issue.
Okay, thank you.
So it's totally fine if the answer for this is yes. I just wanted to check an intuition. It seems like a big assumption or sort of requirement of this is that the functions you're wrapping are pure, so that way it's okay to try them out, find out the contract fails, sort of roll back, and then try the other contract that was applied to them. Is that accurate?
Yeah, so there is the assumption there that they're pure and that it would be okay. if
As
they
I said,
were.
that's fine. I just wanted to know.
It would be kind of, yeah, I don't know if they were side effecting what you would do, because at some point you need to try it out to work out, but yeah. It's kind of interesting, but yeah.
Any other questions? Okay, let's thank the speakers.